All right, so the last topic that we have in this course is going to be on something known as data structures. So we've actually worked with some data structures before. Let me get the notes back up. So let's go ahead and maybe just define formally what is a data structure. And then we'll look at the ones we have, and we'll look at some of the basic ones that are used in more or less any sort of language that are language agnostic over this week. So, Alejandro, can you grab the lights for the screen? Makes it a little bit easier. Appreciate it. All right. So, a data structure is a way of organizing and storing data in a way that we perform operations on the data in an efficient way. So, again, we've talked about efficiency. So, when we're talking about data structures, we're looking at a way of organizing and storing data in a way that we can perform operations on the data in an efficient way. Okay. So let's think about some data structures that we've already encountered. How have we stored data? Go on, throw them out. So we have a type of data. So again, let's think about types of data first then. So data types, we have something that is a string, but a string is kind of a tricky one because a string is really a sequence of chars. So a string is a sequence of characters. So again, a string is basically a very efficient way of storing a bunch of characters. So yeah, you could kind of, that's kind of a start. What else? A dictionary. Yeah, we're not going to talk about dictionaries today. We'll probably talk about it a little bit later. But a dictionary is basically and we'll learn about, it's a more specific type of something known as a hash map. I don't know if you guys have encountered hashing or hash function in any of your courses, but that is a very nice type of data type because of a certain efficiency, it could do a certain type of operation. More on that in a minute. What else? What other structures have we used to store data? Say again? Assigning. So that's, again, storing assignment, but what is, so? A list, that's the big one. There we go, you're getting there. So a list, and of course we also have kind of, so a list was mutable, by the way, just remembering that. You could change it. What was basically a list that was immutable? Does anyone remember? Two of you? A tuple. Yeah. Yeah, so again, we have basically a tuple, which is essentially an immutable list. So this is the big one that we're going to start with. So list. And one thing that we should be very cautious about a list and kind of what it really is in Python is it's more than just a sequence. And again, that's something we're going to look at a little bit. But a list in Python, let me read the statement and then I'll write it, is a dynamically sized array. So a list in Python is a dynamically sized array. So the array is really the more general type of data structure that we're going to start with. And what I mean, this dynamically sized has saved you so many headaches this semester. Let me promise you that. My course that I'm taking right now, we're using C, where they're not dynamically sized, and you have to be very careful about lists or arrays, and I'll kind of talk about why. So again, these are some examples of data. So again, we have a dictionary, we have a list. I'm going to erase this data type, but because a string is kind of a data structure, but it really is its own data type within Python. So these are certain types of data structures. So we see up above, I talked about this little, let's go ahead and underline operations. Let's mostly focus on list. So let's think about list operations. What are some of the operations that we have done to lists or on lists or with lists? Throw them out if something comes to mind. Caroline, I see you thinking. Okay, so we can do addition, which in terms of list was simply concatenation. So you can add lists. What else can you do? You could append something. So we'll just say like append or append or insert into it. So basically add to the list. What else could you do? Say again, Alejandro? So we have ideas of slicing, which is kind of like a type of copying parts of it. So we have like slicing is something that's really only in newer languages. So this is kind of more of the kind of the older languages. This is more of like copying, that you're just looking at parts of it. All right. Okay, so replacing and copying kind of going together. There's a couple other low-hanging ones, Carolyn. So we can delete elements or we can remove elements. So we got to think about this, delete or remove. So permuting them, that's still kind of just copying, moving elements around. There's really another one, I'm surprised. You may have to go back in your brain to access that knowledge. So accessing a data structure, you put elements in it, how do you get it out? So you talked about adding things to the list. So adding lists, this deals with concatenation. And a big one that is kind of important, and we're going to kind of look at a couple of these today. The main ones I want to really focus on today are ideas of like appending and maybe accessing and maybe a little bit about copying. And again, one thing let me just go ahead and Google the list for you, but no pun intended there, but I'll just go ahead, Python list operate, words are not working out there. Python, good thing I'm not typing yet. Python list operation time complexity. Come on, you can do this. There we go. So if you look at a list right here, there are certain things that have to occur when you would do operations. There are a certain number of steps that occur. So again, when we talk about big O, we're talking about the worst case. So you can see here, like copying it is going to be a linear time complexity. And we want to think about why does copying it be a linear time complexity? Anyone have an idea or intuition why would it be big O of n to copy a list? You have to iterate through every element and move it somewhere. So again, the moving might add some sort of constant number of steps, but it's going to at least take a moment. You have to look at every element. Yeah, Kenneth.
K.
K? What do you mean K?
Yeah, like get slice.
Oh, okay. So K would depend on, let's see if it defines up above. Us mathematicians, we always wanted to find. K is either a value of a parameter or the number of elements in the parameter. So again, like a slice, you don't need to look at the whole list. You only need to look at K of them. So K is probably some integer less than n.
Oh, like if you're looking at the K one or something.
Yeah, so you won't necessarily need to look at the whole list. So it's still going to be K is some variable, so it's still linear time complexity. It's just maybe K is some smaller value. Again, another one that's interesting that we'll want to look at is notice that for a list is big O of 1. But like if you want to get the last one, how does it know to get there? And that's something that we'll have to maybe explore. Another really thing that's nice about lists is that you can get an item in constant time. It doesn't matter whether it's the first element, the 7th element, the kth element, or the nth element. You can always get it immediately, or at least not immediately, but in the same number of steps. That's known as random access, that you can access a data structure randomly and find what you need, and it doesn't matter where it is. Yeah, Kenneth.
I would assume that the list is sorted.
these are not assuming that it is sorted. This is just basically if you need to find the fifth element, you just use the bracket notation. So yeah, you're not assuming that the fifth element is the fifth in order. So again, remember, a list is not necessarily a default sort them. So anyway, if you want to sort it, you could do it in n log n time. And of course, if Python, whenever you call the sorted method, the fact that it's n log n means it's probably doing what type of sort? Anyone remember? So it is a polylogarithmic function, but what type of sort runs in polylogarithmic time? It was merge sorts. So again, if you call, because remember in Python you actually have a sort function. So if you wanted to, we'll look at it later. No need to jump around, but anyway, there are a couple other data types and data structures. We haven't talked about a set. This is kind of associated to a dictionary, and when we talk about hash maps. So that's going to be kind of useful to look up, because look at this. This is something, we're talking about hash maps next time. Look at how long does it take to look up something in a hash map or in a set? Constant time. So it seems to be ignoring whether the set is large or small. It could check if something's in there immediately, or not immediately, but in a constant number of steps. It's not going to depend on the size. So that's, again, something we're going to look at. Let's go ahead and go back to the notes right here. And let's talk about an array in general. So one thing before we move on to the first data structure, a list in Python is a dynamically sized array. So it has basically two data structures kind of playing together, and is making Python do things really nicely for you at the cost of speed. It's a very slow language. Like if you were writing something that was performant, like, I don't know, something like to keep a plane aloft, is probably not going to be in Python, because you don't want your programming language to be slow if it's keeping people alive. Just a thought. So let's go ahead and talk about the first one. The first data structure that we're going to talk about is an array. An array is a contiguous sequence of memory that stores a sequence of homogeneous data. So an array, underline array, that's the data structure, is a contiguous, that's a fun word, sequence of memory that stores a sequence of homogeneous, so it's all going to be the same type, data. We don't really have an array in Python per se. A list is essentially a fancier array, because remember, in Python, a list does not have to be all integers. A list does not have to be all strings. It could be int and strings, and that's, again, the dynamic part. The other thing is Python their data is not necessarily contiguous in memory. So an array, let's maybe just do an example or two of an array, is typically in visualized in boxes. So you could have like an integer array. So let's just start one. Let's just do 0, 1, 2, 3, 4, 5. And is in boxes to basically illustrate that in memory, these are contiguous. And we haven't talked much about memory about in your computer, because, it was like, if you think about you're going to buy a phone, how much memory does it have? Well, it has at this point, you're really looking at 128 gigabytes and things like that. An array is storing these in contiguous spots in memory. So in another example of array, let's just say, let me just make an array that this time is 5 units long. So it would be an array of characters. So we'll just do my name. I don't know. We need one more. We'll just do exclamation point. So it's an array of characters. So these are in memory. So we haven't talked much about like what memory actually looks like in this course. Python does a nice job of hiding that from you, but I do want to kind of bring it up briefly and kind of show you the things that are really maybe happening in memory that Python's doing for you, but if you learn C or some other lower level language, you'll have to maybe consider about. So let's zoom in over here. Memory is really visualized as a grid. So if you have, here's just a part of memory. I'm going to just I'm going to use 3 blocks, and then I'm going to go across 8, and I'll talk about why here in a sec. So 1, 2, 3, 4, 5, 6, 7, 8. And we'll just, again, you could assume basically each of these are in a grid. So you could kind of understand memory as a grid. And each of these boxes has an address. So, your address is 1000 Longfellow Boulevard. I don't know, this actually translates really well to the post office or the on-campus mailroom. You go in there and you have your mailbox. I don't remember where mine was. It was like right to the left of the window when I was here as a student. But each of these have an address. So again, you can think about this first one as like address 0. This is address 1, 2, 3, 4, 5, 6, 7. I lost my counting there. Sorry about that. 6, 7. But one thing to note about addresses in memory, and I'm going to so you go 8, 9, but computers work in binary. We talked about this a little bit earlier in this semester, and base 10 does not translate to binary well, and just because if you think about what are powers of 2. So memory typically uses a hexadecimal. So you would actually go A, B, C, D, E, and F. That would be essentially the way you would visualize addresses in memory. And then after F, you would go essentially one number up. So that would be 0 or 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, and so on. By the way, does anyone, I don't know, for anyone who's maybe helped an exploration student, this is like the first lesson in explorations in mathematics. But again, all of what we're looking at right here is hexadecimal numbers. And if you're ever looking at it, like you'll see these preceded with like a 0x. So, this is a lot of fun, just copying 0x on each one. So again, that 0x basically means if you're looking at some sort of Wikipedia page or something later, that 0x means that whatever this number that follows it, this is going to be like a hexadecimal number. So this is a hexadecimal number. In other words, hexadecimal is base 16. So you know how we count to 9 and then we bump up a place value. Again, same principle applies here, except for you count to 16 and you borrow letters to go ahead and do that. By the way, why 8? So if you think about this, there was a reason I did 8 boxes in the grid, and that's because this is 1 byte. So like you have 256 gigabytes of memory in your phone. And again, that's slow memory. You actually even have faster memory and caching and all sorts of fun topics to discuss. I'm just giving you a brief overview. But 1 byte are just essentially 8 little boxes in memory. And this is 8 bits. 1 byte is 8 bits. And a bit, remember, is basically 0 or 1. We talked about this briefly earlier in the semester when you were looking at floating points and representing an integer. You'd use it basically zeros and ones to represent numbers. So this is a little bit of what memory looks like. So let's go back over any questions so far. Yeah.
So a gigabyte would be 1,000.
I always just Google this because let's see, gigabyte. So a kilobyte is 1,000 bytes. So I usually just do 101 gigabytes GB to byte. So yeah, there's a lot. So 128 is, usually you go powers of 2. And you're putting me on the spot, but yeah. So there's a lot. And there's a lot. So there's a lot of zeros and ones in your phone. And that's, again, just slow memory. Again, in an operating course, there's a lot more like how you, I mean, if you think about it, no, I don't want to go into that. That gets too deep too quick. So, fascinating subject. But imagine, let's zoom back in here. So here's our memory. And somewhere in memory, we're going to need to go ahead and put this array. And it needs to be contiguous. So let's go ahead and imagine that I take an array. Let's just do part of it. So I'm going to just, but here is a part of memory. And I want to go ahead and put my, let's go ahead and put 0, 1, 2, 3, 4, 5, right? Let's say that's in memory somewhere. Some program has decided that, like, okay, it's going to put it right there in memory. And then in that same program, we also have my name. So we have C, we have an O, we have a D, because that would be contiguous. We would have a Y, then we have an exclamation point. So what if we wanted to append something to that integer array up here? So what would be the issue if we wanted to append something to that integer array? You would have to move everything of something. So you have a couple. So basically, this is where the computer has decided that that array is going to go, and then it decided this character array is to go here. And if you want to append it, there's a lot of work to be done, right? Like you have to go ahead and you would have to either move Cody like over here, or you would have to maybe like, okay, are you going to want more? So maybe you take all that and move that all the way down here and maybe allocate some extra space. And in a program or language like C, you have to tell the computer exactly like how much space to allocate. So it's a very interesting language to work with, and I would, but it does have a lot of headaches that come with it. And that's one I wanted to expose you to right there. So let's kind of just maybe formalize what we just discussed. So the question I posed is, what if we want to insert 6? Insert 6. Well, you would have to and as Anna pointed out, you basically are going to have to move everything. You're going to have to move everything in memory. And if you, by everything, I mean these elements. So what does that mean in worst case scenario? I mean, you may also have had the scenario like you had like 0, 1, 2, 3, and there was space right there for it, for a fourth element. So, but that would have been the best case. Like you already had space for it. So worst case, you have to move everything. What does that mean is the time complexity to insert, or worst case time complexity to insert into an array? Big O of n. You would have to move everything. So basically what this means is that we have to do big O of n to insert. Or let's just focus on appending for now. Append into an array. Why? Because we'd have to basically copy everything everywhere else. But that's no good. What if we want to access? What if we want to access an element in the array? Well, do we have to do any sort of moving to do that? And again, let's maybe even say kind of what you said. Let's take that assignment idea from earlier. Let's say we have, let's just say, we'll just call it my array. We essentially have some sort of assignment that's pointing to the beginning of that list. So you can go ahead and say my array. And again, we can do something like my array, and we use these braces. This is our access notation. What if we did my array of 3? What is stored in my array of 3? Anyone? Huh? It would just be 3, yeah, because it would be the 0, 1, 2, and then that would be our third element. So my array of 3 is equal to 3. So again, we have an array, we have random access because we have somewhere to start. And then we just say, okay, we need to go 3. Then you just go, okay, you would just basically do some quick little math, and you would go to the third element. So because we have some way to know where it starts. So that'll continue to hold on as we look at other data structures. We have some sort of assignment. So what does that mean? Worst case scenario for access is, regardless of whether you're accessing the third, the first, or the last, is the same. So what does that mean the big O running time is for accessing an element in array? It's constant. So big O of 1 to access an element in an array. And what is this also relying on? It's contiguous in memory. Contiguous, in a line, continuous. So so it's just simply referred to as contiguous memory. So basically 0, 1, 2, and then you don't jump over here for 3, 4, and 5. So if you tried to access the third element here, it would be like, wait, that's not part of my list, or my array in this case. So contiguous means they have to be in a line. All right, so the big issue is, how do we deal? Is there something that we can do that just basically makes appending cheaper? Is there something that we can do where we can actually make appending something right to the end of the list, basically ignoring what else is around it? Is there any ideas? What can we do to maybe make this constant time? Any ideas? Ask your neighbor, any ideas? Is there a way that I could set this up where I do not need to go ahead and worry about if it'll clash with something and I have to move anything? Any ideas? Right. Anyone have any ideas? Let me ask for volunteers. Kenneth, what's your idea?
So like if you know that you want to append like the numbers, right?
Okay. Yeah,
So you know that the array length of the numbers is like 6.
Okay.
So if you could look at like the 6th element and then split it into 2 arrays and then append it to the first array and then concatenate them again.
Okay, so there's this idea of like, I want to just go ahead and put 6 here, but let's see if we could split it. And maybe, what if we put 6 here, but we need a way to, and I think what was that last line you said?
Concatenate.
You want to concatenate those. You want to link them together. So it would be nice if I could basically link it right there at the end to some other part of memory. Then I wouldn't have to copy it. I just have to know that there's a link between them. And that's the next type of data structure. It solves this problem where inserting takes a linear amount of time, and it makes inserting at the end, and we'll talk about inserting in the middle, how that would be different, but it would make it inserting at the end or appending constant. It doesn't matter how long your list is. If you want to add something to the end, you could do it in the same amount of steps. And that right there is known as a linked list. So I'm going to go ahead and show you kind of graphically or visually what a linked list is, and next time we'll kind of code it up and kind of make sure we know how to represent in Python. All right, so let me go ahead and add up the next page. The next type of data structure that we want to look at, and I'm going to just kind of show it to you and then we'll explore it more next time, is a linked list. So a linked, not linked, list is a sequential structure. So notice it's not contiguous this time, it's still sequential. So it is a sequential structure that consists of a sequence of items in linear order which are linked to each other. All right, so I'm going to cheat actually. So because my writing gets very sloppy, don't look ahead. I'm going to just cheat and copy and paste. All right, so I am so fast. All right, so, and let's make this a little bit easier to read. And there we go. All right. A linked list is a sequential structure that consists of a sequence of items in linear order which are linked to each other. So we have our integer array, and we know in memory it is contiguous, 0, 1, 2, 3, 4, 5. Those are right next to each other in memory. The big issue we ran into was if we want to append 6 at the end, and we already told our program you only get these 6 spots, well, it would maybe have to move everything it would have to reallocate that. So let's go ahead and look at our memory again. Again, as memory you could kind of picture as a grid. 3, 4, 5, 6, 7, 8. And the way a linked list works, let's say so this is an integer, this right here is an array. So a linked list would look more like this. Let's say 0 is right there. Let's say 1 is right, or let's say 1 is right here. 2 could be next to it. 3 can be over here. 4 can be over here. Actually, I want to rewrite 2. I want to write 2 right there, and I'll think about why in a sec. And then we would ultimately have 5, something like this. So there's the same elements in my array, but they're not in contiguous memory. So how do I know that they're still sequenced? I want to. And the way you'll do that, and C would call a pointer, we've called it a reference in this course. We basically have to store an arrow after each pointer saying where to go to next. So this right here is the linked list. Anyone see any downside to this? So it solves our problem. We can now, if we need another element in our array or in our whatever we're trying, our linked list, we can put it anywhere in memory and draw an arrow to it, right? But what is the downside to what I just did? And you can maybe see it the way I drew the arrows.
Really complex fast.
It's going to get really complex fast, and we'll kind of even see that when we code it up next class. Let me draw this. Each element in this structure is going to take 2 spots in memory. 1 spot for the value, 1 spot for the arrow, which we'll call a pointer, as you'll probably, so you can see right here that each element in the linked list has 2 properties, the value and then a pointer to the next element in the list. So what you'll maybe do is look at this visually. What time is it, by the way? 2:40. You know, I kept looking at 41, and I'm like, I only have 9 minutes left. And I'm like, I've had 9 minutes for the last 20 minutes. For some reason, I thought we were about out of time, but I really have about 10 more minutes. That has confused me so badly. I'm like, oh man, is it time to go? I only had 9 minutes. Then I realized, oh, that's the wrong time. So someone remind me, like, when it's like 2:48, or don't, and we'll just have class till like 7 o'clock tonight. I don't know. I don't have that much material, so it's like a bad comedian. I don't have that much material. Okay, let's keep going. All right, so that's the way it's laid out in memory, but let's go ahead and just zoom in over here. The linked list looks like this, that each element, so we would have 0, and then you would have a pointer to the next element in the list. So let's just visualize this right here as follows, and that would be 2. That would be a pointer then to 3, and I should have made my linked list smaller. Oh well. This is good practice in emphasizing that there are 2 parts to each node. And I'll do this. So again, these right here are sometimes referred to as nodes in the linked list. This right here is sometimes referred to as the head of the linked list. This right here is the value of the node. So you could think we have node.value. And in Python, we typically call this next, but next is just a pointer to the next node. So this is node.next. So you could kind of see, and then we're going to program this up next class, a linked list is going to be a sequence of nodes, and a node is going to be its own class that has 2 pieces of data. Okay, so by the way, a little bit of terminology, I'll sometimes refer to this right here as a pointer. And again, what is that pointer really doing? So maybe just to kind of talk about this in terms of memory, we can say like this 0, I'm really zooming in here, sorry. So let's just say this is some arbitrary spot in memory. Let me make my pen really small. So let's say in memory this is like 0x123. No, let's just do 1, 2. So this would be, let's say this is at 0x23. It's not contiguous. That 1, 2 is not next to 2, 3, agree? So what this pointer is basically storing the location of the next node. So that's the value of next, is going to be a pointer to wherever you need to go in memory to find the next value. This is again known as a linked list. So just to see if the idea is stuck, let's say this right here, that is 0, this in memory, let's say that's at 3, 4. What would go right there? 0, 3, 4. It's going to tell me where to go in memory to find the next element of the linked list. Yeah?
So the last element of the linked list would not point to anything until...
Yeah, exactly. So this is something we're going to want to be careful of when we code it. So let's go down here to the last element. What goes here? Well, what typically goes there is like something, this in C is called the null pointer. In Python, we would just call it none. So remember, we have a certain keyword in Python called, what do functions return? If you don't specify, by default, they return none. So in Python, what we would put here is a pointer to none. And none is like a special spot in memory, like the interpreter knows how to deal with, like, this is none. Like, it has its own properties, such as the lack of existence and things like that. Let me see if there's anything else I want to say. Oh, okay. So how are we on time? Perfect. 5 more minutes. So to close things off, let's about kind of the conceptual part about linked lists. Let's talk about appending. Let's more specifically the cost to append. Well, let's say you have, I'm going to just make a smaller list here, so yeah, let's just make a smaller list. So let's say we have 0, and then this points right here to 1, and then this points right here to 2, and this is, as you point out, pointing to null. Well, if you want to append to the list, realize you don't necessarily care if it's contiguous. How would you do it? You would create a new node anywhere you want. So let's call it 3. And no, just to emphasize, it doesn't even have to be a number. Let's say what's someone's favorite number? 7. Boy, you guys were math majors, all really excited about numbers there. Like 7, I guess. So 7. You would create a node with value 7. It would be pointing to, none if you want. And what you would have to do is you would just go ahead and just grab that one and point to that one. How many steps did that take me? 1 to create. Granted, it might be more, but 1, let's just assume 1 to allocate, and then 1 to new point. And does it matter if I have let's say this was 1,000 links long, would it take more time to append? No. So what does that mean is the cost to append? Worst case. Big O of 2, which is the constant. So yeah, it's going to always take the same number. It doesn't matter if the linked list has 1,000 elements or 2 elements or 3 elements like right here. The cost to append is big O of 1. But what if you want to go ahead and find or access an element in the list? It's not in contiguous memory anymore. So what do you have to do? What is the cost? The cost to, let's say, access. Anyone think they know? Kenneth, I heard from a lot from you today. Let's see if anyone else. Alejandro, what do you think? You're looking tired back there.
Big O of N.
It is big O of N. Why?
I don't know how to explain it.
Okay, that's fine. Anyone think they could explain it? You can do math. It's not like I can just look at the 10th element and realize that it's not contiguous anymore. You have to traverse each link. Worst case scenario, you're trying to access the last element, so you have to go through every single one. There's no random access with linked list. So the cost to access is big O of N because I'll just say we need to traverse the linked list. I'll just say the entire linked list. And again, remember, big O is worst case, so you need to access the last element. But look at the big kind of the big picture we looked at right here. Linked list, we have cost to access is linear, but to append, and think about it, a lot of what we deal with today in terms of computing system is adding data. Like big data, you're adding information to this. It would be nice to have some sort of data structure that actually allows you to quickly add something to it. So the cost to append is big O of 1, and the cost to access is big O of N. Does anyone remember for an array, what was it? Well, in an array, what we talked about above, right here, what was the cost to append? Big O of N. What was the cost to access though? Constant. So computing is one of those things you never get anything for free. If you want to improve one thing, it's probably going to cost you something somewhere else. So this is a case of, it's basically the ability to lengthen it costs us the ability to quickly access it, and vice versa. So that's something that we're going to look at more next time. Let me see if there was anything more I wanted to go ahead and talk about here. Does anyone have any questions? Okay, so yeah.
So this has to be sorted for you to do the linked list.
What do you mean sorted?
Like
the elements do not need to be sorted. That's why I try to make the 7. Okay, one to clarify. I think we just were dealing with things to sort it. They didn't have to be sorted. This could have been 1. This could have been 5. But then that's a good question. How long would it take to sort? Right. How long would it take to search? And that's kind of where we would go if we wanted to go deeper into this. By the way, Python lists is a combination of both of these. Because they're doing the dynamic allocation using pointers, but they have some parts of that list that are actually arrays, so you have the quick access. So there's a great book for anyone who's curious about the inner workings of Python called Fluent Python, but it basically talks about a lot more of how the actual things we've talked about are implemented in a way that is efficient and things like that. Haven't gone through it entirely, but it's on my to-read list after I'm done with grad school. But if you have any questions, feel free to stick around. We will code up a linked list and talk about some other data structures as we go through this week. Remember, Project 5 is due Wednesday, and I'll get Project 6 out to here pretty soon. And don't forget to think about what you would like to build. Begin choosing your own adventure. Okay, I'm done rambling. Have a great day, everyone.
So I have to go to the bank right now at 3.
Okay.
That's why I can't